set up. Let's get started.
Oh, yeah. So,
good afternoon. It is my pleasure to introduce Victor and Ángel. Just a brief bio of what they've been doing or where they've been. Victor is a postdoctoral fellow in our department. He has a PhD in atmospheric sciences from the University of Sao Paulo in Brazil. Nice. He's also visiting professor at the La Agraria La Molina University in Peru and the University. Victor's research interests are broadly in large-scale atmospheric dynamics with a focus on tropical meteorology. He has performed research in tropics such as the Madden-Julian oscillation, Kelvin waves, interannual variability over the Pacific and Atlantic Ocean, and paleoclimatology. And just a fun fact about Victor, today is his birthday, so happy birthday. Happy birthday. So Ángel I've known since forever. He was originally my lab partner at the University of Puerto Rico, so I have a couple stories to tell them that day. So he got nervous immediately.
No, I'm not nervous. I'm looking at you with like a challenge me face.
So Ángel Francisco Adames-Corraliza is originally from San Sebastián, Puerto Rico. He got his bachelor's in physics from the University of Puerto Rico, Mayagüez. That's where we met. He then got his master's in science at the University of Washington. He did his postdoc at GFDL and was an assistant professor at the University of Michigan before he got poached. This is his words. Here at the department. So, of course,
The rest of us pulling those strings from the very beginning. Playing the long game.
Can you get the lights? Can you get the lights?
All right. Well, good afternoon, everybody. Welcome to the talk. We're going to split this talk in half. So this is part one, part two study that Victor and I have collaborated together. We think that these are some of the most interesting results that we've gotten in our 2 to 3 year collaboration. But I don't know how long we've collaborated, but I think this is actually one of the best stuff we've done. The first half is going to be Victor's part of the two-part study, where she's done most of the analysis and results, and then the second part will be the theoretical implications of these results that Victor got. So, welcome everybody. Victor, take it off.
Okay, and thank you, Ángel, for the presentation. As Ángel said, we decided to present today our most recent work, and we decided to put this really, provocative title, The Stirring Tropics. And as Ángel said, I will present the first part of the work, and Ángel will present the second part of the work. Okay, I'm going to start showing this animation of brightness temperature, which is used in this work as a proxy of convection. And when you start looking at this animation, maybe you will see that a convective organization basically over the tropical domain are apparently chaotic. But this is because the tropics contain a diverse water system with a wide variety of spatial and temporal scales. For instance, this system, can be composed by, convective coupled waves, such as Kelvin waves, Rossby waves, wicks, TDs, and of course the Madden-Julian oscillation. As clear showing this space-time spectrum of the brightness temperature, the same which was shown in this animation. And if you extract the information of these, of these waves and plot together in this animation, you clearly see that in fact, a large portion of the convection organization of the tropics is in fact fairly well organized by the Madden-Julian oscillation, which is propagating eastward over the tropical domain, in fact, impacting precipitation, not just over the tropical region, but also higher latitudes for the tropical and subtropical teleconnection. In the same direction, as shown in this space-time spectrum, Kelvin waves is propagating eastward, organizing as well convection. If you go away from the equator, you can also see a type of tropical depression system, such as this monsoon low pressure system over the Indian Ocean region, which is organizing convection over this domain. So all of these convective systems, based in many previous works, can be classified in two main groups or two main regimes. One is unbalanced regime, and the second is balanced regime. So what exactly is that regimes? So the balanced regime, a perfect example for this regime represent, for instance, inertial gravity waves. For instance, here I'm showing 2-day waves over the Amazon region. This is the horizontal structure, and we can see the main characteristics of this imbalance regime. First of all is the short time scale of these disturbances. Second is the fast propagation of these disturbances. For instance, these 2-day waves over the Amazon propagate at about 35 meters per second over this region. And finally, temperature fluctuation play a key role in the thermodynamics of these disturbances. Okay, on the other hand, we have balance regime, and a perfect example for this balance regime, for instance, represents the Rossby waves. I'm also showing these Rossby waves over the western hemisphere. This is the structure in the lower troposphere. And what characterizes this balance regime, first of all, is long time scale. Well, if you compare this one, it's really a long time scale, these Rossby-like waves. Second is the slow propagation of these disturbances. For instance, these disturbances over this region propagate at about 5 meters per second. And finally, in this balance regime, moisture plays a central role in the dynamics and thermodynamics of these disturbances. Well, as you probably notice here, I highlighted 2 main features in this balance regime. First of all, slow propagation, and second, moisture playing a central role in the dynamics of these disturbances. So why I mentioned that? First of all, because these convective coupled waves, which you saw in the animation, are often viewed as an extension of the dry waves. This is the dry wave dispersion, which are reduced in equivalent depth to represent moist convection. But the question is if this theory accounts for the all observed structure observed in these disturbances. And maybe the answer is not. And for instance, the Julian oscillation and TP wave disturbances represent a clear example that these disturbances have some, this theory have some limitations. Okay, let's move to the tropics. So what happened over the tropics? What makes special the tropics? We can say that there are 2 main features that characterize this tropical region. The first one is the weak temperature gradient observed over this domain. As observing this climatological temperature at 700 hectopascals, you can see that over this domain, temperature is pretty homogeneous and changes little in time and in space. The second feature is that large moisture fluctuation, which was observed over this domain, that in fact shapes and drives the wave activity over the tropical region. So these 2 main features give us one important consequence. In this case is the existence of moisture modes. So what exactly is moisture modes? So if you're not familiar with this term, if you're not taking tropical dynamics this semester, we can easily define like a type of tropical motion where the water vapor play a central role in its dynamics. And of course, these moisture waves don't exist in the dry theory. Okay, so what exactly constitute moisture modes? So based on these 2 previous studies, Ángel 2021 and Mayta 2022, proposed 3 criteria to identify moisture modes. So what exactly says the first criteria? The first criteria says that to have moisture modes, in fact, moisture anomalies must exhibit a high coherence with precipitation anomalies. In other words, these 2 terms should be highly correlated with each other. This is the first condition. The second condition says that to be considered moisture mode, in fact, the wave must be in weak temperature gradient balance, or a balance between the adiabatic cooling and adiabatic heating should be true to be considered a moisture mode. And finally, the 3 criteria said that the thermodynamic variation in the wave must be dominated by moisture. Or in other words, the contribution to moisture should be much larger than temperature variation. Okay, this criteria is pretty easy to be tested. You can apply in observations, in reanalysis, and model outputs. Okay, by using all of these 3 criteria, we documented for the very first time the existence of moisture modes, but in this case outside the Whirlpool region, in this case over the western hemisphere. Okay, let's see in detail where we found this moisture wave. So here I'm showing the variance map of precipitation of brightness temperature, or in this case filtered in the Rossby wave domain. As you can see, these disturbances in fact are more active over the Indian Ocean region, over the Western Pacific, and not much signature is observed over this region. But we explored these Rossby waves over this hemisphere. And this is basically showing the horizontal structure of these waves over this domain. As you may see here, this structure closely resembles which was predicted from the theory. But there is some problem. This wave propagates pretty slowly. It's about 5 meters per second over this region. This slow propagation is in fact can be explained when you use just the tree theory alone. Indeed, if you use the criteria, you also discover that in fact this wave is a moisture wave. Okay? We can also use this additional criteria, call it the end-mode parameter, to classify if our wave is or not a moisture mode. This end-mode parameter, by definition, is basically a non-dimensional parameter that measures the relative contribution of moisture and temperature in the evolution of moist enthalpy. Well, to have moisture mode, basically this end mode should be much less than 1, or in other words, the contribution of moisture should be much larger than temperature contribution. A more strict definition of this end mode can be given by the following equations, which include basically the phase speed propagation of the wave, temporal time scale, the convective adjustment time scale. Okay? We can also plot this end mode as a wave number frequency, as shown in this figure. So, what exactly shown in this figure? This, in this case, is a regional space-time spectrum calculated just for the Western hemisphere. In this case, the contour represents the spectrum of the brightness temperature or precipitation, and the shading is showing the end mode parameter. So what does the shade correspond to? So everything that's in blue in this diagram are moisture modes, or where the moisture played a big role. The white region here represents the mixed waves, or where temperature and moisture play similar role. And the yellow represents basically the gravity waves region, where temperature fluctuation basically play the main role in these waves. Okay, so if you see here, so this is the description of the Rossby wave, the observed Rossby wave. You can see that large portion of this spectrum falls into the blue regions, which means that this wave can be classified as a moisture mode according to this end mode parameter. Okay, this is another way to demonstrate that our disturbances over the Western Hemisphere is a moisture mode. However, when we are analyzing these Rossby waves over the Western Hemisphere, we discovered a second potential moisture wave, in this case, which corresponds to the TD wave disturbances. As you observe it here, a large portion of this TD fall into the blue region, which means that many of these TD waves, in fact, are moisture modes. Okay, to analyze in detail, here again, I'm showing the TD variance, in the whole tropical region, and we explored these TD disturbances over the whole tropical region, or where the maximum variance in this TD brightness temperature is observed. Okay, let's start with TD disturbances over the Atlantic region. So this is the structure of these disturbances at the lower troposphere. In the previous paper, actually we demonstrated by using this criteria that these disturbances is a moisture mode. If you go to the Eastern Pacific, this is this structure closely resembles to the Pacific easterly waves. Rosa is analyzing in detail this wave, and she also found that these disturbances also can be classified as a moisture mode. So if you go to the Western Pacific, this is the structure of this wave at the lower troposphere, and also applying the criteria, we discovered that this wave also is a moisture mode. Finally, we have over the Indian Ocean region. This structure also resembles to the monsoon low pressure system over the Indian Ocean region, or over the Bay of Bengal. HE also is analyzing in detail these disturbances, and also he found that these disturbances satisfy the all criteria to be considered a moisture. In conclusion, these TD-like waves are moisture modes over the whole tropical region. Okay, let's analyze, well, using any mode to confirm if these two waves are moisture modes in the whole tropical region. So in this case, we basically divided the whole tropical region in three main sectors. I will start with the Indo-Pacific region. Remember that everything in blue here, according to that mode, is a moisture mode. This is for the Indo-Pacific region. Here I'm showing just for the negative sonar wave number. If you see here, you can see that equatorial Rossby waves and TDs, a large portion of this spectrum fall into the blue region, which means that these waves are in fact the moisture modes over the Indo-Pacific region, which was also expected. If you go to the Western Pacific and Eastern Pacific, again you can see that a large portion of the equatorial Rossby waves and TD fall into the blue region, again, which means that these disturbances are moisture modes. And finally, as we saw previously, over the Atlantic region, these disturbances, so a large portion of these disturbances fall into the blue region, which means also these disturbances can be classified as a moisture mode over the whole tropical region. In conclusion, these two disturbances, Rossby waves and TD waves, are moisture modes in the whole tropical region. Okay? Right. So up to this point, I hopefully convinced you that moisture mode exists and occurs in the whole tropical region. So now we basically explored what process control the growth and the propagation of these moisture modes. For this, we used an observation, in this case from red analysis, era 5, and also used a theory. Ángel will explore in detail this second part. Yeah.
Victor, before for the plots that you just showed, what data are you using
Oh, which one?
for the plots?
All of them comes from red analysis. Sorry, I didn't.
The analysis,
Yeah.
era 5?
Era 5. Yeah. Okay, so considering that moisture static stability is highly correlated with convection, we can use, well, the MC budget to understand the evolution of convection in these moisture mode waves. This is the whole equation for the MC budget, basically composed by the advective terms and the source terms. Okay. Let's start with the contribution to, or the mechanism responsible for the propagation of this moisture mode. This can be considered an average for all moisture modes we was showing in the previous slide. So here, the bars in this figure, the bars basically represent how much each term contribute with the propagation of this wave. So in this case, as you can see, there are many bars, but for instance, here I'm showing for the Rossby wave, the evolution from day minus 8 to day plus 8. And the red circle basically means where the wave is showing the maximum amplitude or like 0. Okay, this is basically describing the entire life cycle of the wave. Of course, there are many terms which are contributing with the propagation of the wave, but I will highlight just one which is mainly responsible for the propagation of the wave. As you can see here, the propagation of this moisture mode is basically due to the horizontal advection of the moisture by the midwall. Or we can say that trade waves basically propagate these moisture modes. Okay, the same happens for the Rossby waves and TD-like waves. Okay, if you analyze which term contribute with the growth or decay of this wave, again, I'm showing for reanalysis era 5. In this figure, the bars again basically showing how much each term is contributing with the growth or decay of the wave. So here, positive values means contribution to the growth of the wave. Negative values means contribution to the decay of the wave. Okay, let's start analyzing these two terms. The long wave radiated heat. As you can see, during the entire evolution of this wave, this term is basically showing positive values, which means these terms are always contributing with amplification of the wave. In contrast, if you analyze this vertical advection of moisture, you can see it's always showing negative values, which means that this term is contributing with the decay of the wave. In addition, these two terms are actually the same magnitude, which means these two terms are trying to cancel each other during the evolution of the wave. So the main consequence is that the main consequence of these terms is that the horizontal advection basically play the main role in the growth and the decay of the wave in a process which was called the Moisture-vortex instability. In this instability, okay, this term B prime basically is the anomalous meridional winds basically advect the moisture towards the system. In this case, contributing with the amplification of the wave. Okay, so this term within the previous basically contribute with the propagation. Here are contributing with the decay of the wave. Okay.
Could I ask how QR works? I've heard that for tropical cyclones that if you have some clouds, that it'll trap up well in infrared and sort of give a feedback maybe. How do you envision that the QR part working, the net heating?
You say the physical mechanism of this?
Yeah.
Yeah. So you can understand this term. Why this term contribute a lot with the growth of this system is because the upper level cirrus clouds, which is basically acting like as a blanket, trying to basically import moisture into the system. You can understand this. This right? Yeah.
So it's like reduced radiative cooling to space because you have clouds.
And cirrus instead, I guess maybe in a tropical cyclone, there's all these deep clouds.
Yeah, any kind of clouds.
Roll that infrared out.
Any kind of clouds, the higher up they are in the atmosphere, the more.
Yeah. Okay, so here, the main conclusion of this one, we can say that moisture modes are largely controlled by the horizontal MC advection. Okay, the obvious question, in fact, here was if this MBI process is the same in the whole tropical regions. To answer this question, here I'm showing TD waves in the whole tropical region, and we analyzed the contribution of this horizontal advection in all tropical disturbances, which analyzed previously, and we can see that, for instance, that in the whole tropical region, we can see that the trade winds basically propagate the wave. You can see there is over the Atlantic region, Pacific region, this is over the Indian Ocean and over the Western Pacific. Of course, there are some differences because the wave is not propagating over the same region. So the terms that contribute with the growth or decay of the wave, again, you can see this term, B prime, basically advecting moisture to the system, is basically playing the main role in the growth of the wave. Okay? The same is observed in the whole tropical region. So what are the consequences of these results? Okay, now Ángel will continue talking with this.
Am I supposed to?
Yeah.
Okay. All right. So I take it that the next slide is what follows from this contribution. So summarizing what Victor just said, the important thing that we're going to talk about from here on is these two highlighted terms here. So it looks like from these four different basins that tropical depression-like waves are being propagated westward by the trade winds. So it's this term here, U bar, the EDX of the anomalous kinetic energy anomalies. We do note that there are, the meridional advection term can be important in different basins, but we see that the common feature is this trade wind term here. And then this meridional MSE advection by the anomalous winds are always contributing to the growth of the TD-like waves, especially when the wave is growing, which is when this DT of moist-static energy is positive. So this is the growth phase, and these are the decay days, and you can see that in the growth phase, there's always a positive contribution to the growth of the system by this, what we were going to refer to by the moisture-vortex instability, which is the advection of mean-state moist-static energy by the anomalous meridional winds. So a hypothetical model is that if you take this green at face value, it must mean that all these tropical depression waves, including also equatorial Rossby waves, they must be stirring moisture in the tropics. So here, to give you a little bit of intuition of what I'm going to be talking about in the next couple slides, imagine these are mid-latitude cyclones up here. and the mid-latitude cycles grow by baroclinic instability, and we know that one of the consequences of baroclinic instability is that they're stirring temperature in the mid-latitudes, bringing warm air from the subtropics out to the polar regions and cold polar air down into the subtropical regions. So they mix that out, and as a result, they actually flatten the temperature gradient that you see in association with the thermal wind. Now, our hypothesis is that a similar analogous mechanism occurs in the tropics, but instead of talking about temperature gradients, we're going to be talking about the horizontal moisture gradients. So we're going to be seeing that all these waves are they like to preferentially develop over the region where the horizontal moisture gradient is strong, and not necessarily where the moisture distribution is very high. So not necessarily the most moist regions of the tropics, but the tropical regions which are sufficiently moist for convection, but have a strong enough gradient for this stirring mechanism to occur. As a consequence, our hypothesis is that tropical depression waves and equatorial Rossby waves, which are collectively moisture modes, that the moisture modes are actually stirring the moisture in a similar way as in the mid-latitude eddies, but instead they're bringing dry subtropical air down into the equatorial area, and then they're bringing moist equatorial air up into the subtropical area. So in order to think about this a little further, this is a diagram from Rios Berrios et al. In 2020, and they show the zonal mean eddy heat flux. So if you have the stirring mechanism, one of the consequences is that there has to be a mean eddy moisture flux away from the equator into the polar regions. And this diagram has been shown by many studies, but I think there hasn't been a lot of emphasis as to what is going on in the tropical area. So let me start by the zonal mean eddy heat flux. So the eddy heat flux, as you would expect, is very large in the mid-latitude regions of both north and southern hemispheres. So you see that these are different models. This blue line here is idealized aquaplanet storm permitting model that NCAR is running with the main office of the study, and these are different free samples of CMET6 models that are being used for reference. So all of them have heat flux towards the pole. Yeah.
Quick question, have you separated out the time variability versus spatial variability in this eddy?
Yeah, they're like in the study they
So
talk
this
about.
is all the time
Yeah, this is all
variability? It's
yeah.
it's not spatial variability.
Yeah. So this is like eddies, not zonal mean and not mean state. So it's just temporally varying eddies. Yeah. So you see that in the tropics, the distribution of the eddy heat flux is pretty flat. There's pretty much no heat flux from 20 degrees south to 20 degrees north, which is this box over here. In contrast, you have a zonal mean eddy moisture flux that is actually increasing away from the equator already in the tropics and reaches a maximum amplitude in mid-latitudes. However, the thing that strikes me as really interesting is that if you look closely at this line here, you see that the blue line here, which is the storm permitting model that they use, it climbs up and then it plateaus from roughly 15 to 20 degrees. And if you take the divergence of this and take the DDY, that means that there has to be an eddy moisture divergence near the equator, but little to no divergence over here, and then the divergence picks up in the subtropics. So this gives us the hypothesis that whatever is causing the eddy moisture divergence in the equatorial region might be different than what is causing the moisture divergence in the subtropics. Maybe it's a different set of waves. So is that what we're going to see, yes or no? Or can we explain this flux using simple theory? So that's what we're going to be doing for the next couple of slides. So what we're going to do is that we're going to take a model similar to that in Chapter 7 of Holton. So it's a two-layer model. We're going to relax the quasi-geostrophic assumption of it and instead use the weak temperature gradient approximation as our starting point to developing this model. Our model is going to be based on rigid lids at the surface and the tropopause, and then we're going to have two additional rigid lids, one in the upward branch of the Hadley Cell, which is going to be this cloud here, and then one in the edge of the downward branch of the Hadley Cell. So this is going to be a self-contained Hadley Cell model in which you have easterlies in the low levels, westerlies in the upper levels. This is the upper layer here, this is the lower level here, and then you have this overturning circulation over here that describes like an idealized Hadley Cell. So we're going to linearize this Hadley Cell, and we're going to get a set of equations based on this and see what the wave solutions look like and what the interactions between the mean state and the eddies look like. So this is just, the same one that I used in Adames 2021, which I gave a talk like 2 years ago here about it, and we just edited around until it makes more, is more similar to a tropical overturning circulation here. So So you see radiative cooling here, the colors here, the brown colors means dry, and then the blue colors here mean moist. So we're also going to be inserting a moisture gradient where the moisture is a peak up here, and then it kind of gets drier as we move down to the subtropics. The reference latitude here, y equals 0, is going to be roughly 15 degrees of latitude, and then the ITCC is going to be locating this minus LH, which is a half-width of the Hadley cell, and then LH is going to be the poleward end of the Hadley cell. This LH half-width is going to be pretty important moving on, as we will see. So this is our linear set of equations. If you don't and not a super fan of math, we can describe this fairly quickly in terms of what the processes mean. So it turns out that under the weak temperature gradient approximation, the upper levels don't play a big role in the dynamics of the system. Instead, you get a pair of equations for the low-level vorticity, which is this theta 3 here. This is 3 corresponds to layer 3, which is the lower free troposphere. Then the terms that describe the evolution of the anomalous vorticity are the zonal advection by the trade winds, which is this term over here, and then vortex stretching by having a lot of moisture in the column and hence a lot of convection, plus radiative heating, which is this 1 plus R term that you see here. The other equation that goes up is the column integrated moisture budget, which is essentially the same as the mostatic energy budget that Victor was just talking about. So you have the tendency, and then you get advection by the trade winds, which is this U3 value here, and then you got meridional moisture advection, which is the mechanism that Victor described as the one that's responsible for the growth of the moisture most in the previous slide, where we know that the advection term here corresponds to the propagation of the waves. So we're going to take this system of equations and then we're just going to solve it, knowing that we have mean trade winds that are going to the west.
I know.
Yeah.
I always stumble over this, I'm sorry. W prime, you just said that that's a moisture anomaly.
Yeah, that's a column integrated moisture anomaly. It's capital W. Yeah.
Okay, it's not vertical motion.
It's not vertical motion.
And how does it do stretching?
So
It is vertical motion.
it is vertical motion, yeah. It is vertical motion under the weak temperature gradient approximation. Areas that have high moisture have precipitation and has vertical motion. So you can interpret this as vertical velocity as
So
well.
anytime you see a 30 max, you know it's raining under the weak.
Yeah, pretty much.
That's-
A column integrated theta E would be.
There's no middleman for forcing of that vertical.
No, it's just gonna happen because it wants to happen, because that's where you have the least amount of like entrainment and dilution of the clouds of that layer. So it's just ripe for convection to happen in that region overall.
Okay, thanks.
Yeah. Okay, so here's the structure of the waves. Here we're showing rainfall anomalies. So blue is enhanced rainfall, and then the brown is reduced rainfall. So going back to John, the blue here would be upward motion, the brown is downward motion, and this is also the area where the motion is upward and downward as well. So this is the upper level stream function. So this is for the upper troposphere and this is for the lower troposphere. The first thing that I want to mention is that when you solve this safe system of equations, you get a wave that has a very weak signature in the upper troposphere, but a fairly strong signature in the lower troposphere. So you see these low pressure systems that develop these high pressures. The low pressures have high moisture to their east or slightly to the east of the center. This depends on the mean state. Remember that the moisture is the maximum down here, and it's a minimum down here. So you can imagine that the waves are pulling high moisture from down here and then bringing it up over this where the southerly winds are strong in the moisture most that you get solution from here. So you can imagine this as being some kind of wave solution where the main dynamics are occurring in the lower troposphere, and and they're really driven by moisture fluctuations. Now, it's worth noting that the most unstable solutions are pretty circular, and they're kind of reminiscent of tropical depressions. That's something that is an interesting finding, and we don't have an answer to as yet, but we've been talking to colleagues which think that there might be a relationship here associated with these systems as well. So these are the wave solutions of the system, and if I try to simplify it as much as I can in order to get the main findings in here so that you all can appreciate the main result here. So this is the dispersion relationship. The real component of the dispersion relationship contributes to the propagation of the system, whereas the imaginary component contributes to the growth and decay of the system. Now you're going to see here that the real component is going to be, a lot of it is going to be this U3 bar times K. So this is actually just the advection of the moisture anomalies by the trade winds. So this is just the term that Victor found that is associated with the propagation of the waves. We have the second term here, which is very interesting and somewhat more complicated. So it's a square root. So there's a plus minus here because our solution to the wave equation is actually It's a quadratic formula, so solving the quadratic formula gives you this plus minus sign. And then in here you get an imaginary number. You got this beta q here, which for those of you that like think in terms of mid-latitude dynamics, this is essentially a beta effect, but just from the moisture gradient. So the moisture gradient in this framework works like a beta effect. In terms, you can write this in terms of a vorticity gradient, so you can think about it a little bit more clearly. Tau c is the convective adjustment time scale, and then this k squared is the horizontal wave number. It is important to note here that this looks a lot like a Rossby wave solution. But instead of having the Rossby wave actually contribute to the propagation, you see it that it's multiplied by an imaginary number, it's on a square root. So that means that this term is actually contributing to the growth and decay of the system, and as well to the propagation because of the complex number characteristics of the system as well. So if you look at the growth rate here, you see that the brown line here is the growth rate, and you see that the growth is a maximum at solar wave number 10, which is the tropical synoptic scale. So these are the scales where we see a lot of tropical depressions form, and you see that the growth rate is generally positive throughout this whole wave number frequency domain. So we see that they're affected by trade winds, and then meridional moisture gradient contributes to the propagation and growth. Now there is something a little bit interesting going on in here. And that is this plus minus sign, because the solution is actually quadratic. And the quadratic solution means that because you have a plus minus sign, even if you reverse the moisture gradient and give a negative sign to this, or if it's positive, you're always going to get a growing solution and a decaying solution, because you always have a pair. And one of the pairs is going to be growing and the other one's going to be decaying. So there's always going to be an unstable solution to the system, regardless of what the moisture gradient here looks like. So the net result of this is that the moisture gradient has to be unstable. And in fact, it's always unstable in the presence of background rotation. There's actually an implicit planetary vorticity plugged into this beta effect here. So the net result is that all these regions that I pointed out with the little rolls are in fact regions that should be, according to the linear theory that I presented here, these are regions which are unstable. And the only regions that we haven't highlighted are these regions of moisture gradients down here, which are right at the equator. There's no planetary vorticity there, so we don't expect these regions to particularly be unstable, but all the other ones that are highlighted should be, and as we will see later on, are actually in fact unstable. So if you are familiar with wave mean flow interactions and the general circulation, we can actually write all of this in a summary form as interactions between the Hadley cell and the moisture modes. So what we're going to do is that we're going to look at the moisture variance, which is just W squared. So this is like essentially the variance of the vertical velocity, for those of you that think about like John. And we're going to call that the wave activity. And the reason that we call this the wave activity, for those of you that have seen quasi-geostrophic interactions between the jet stream and the baroclinic waves, is that the moisture behaves like a potential vorticity does in the mid-latitude. So wave activity here is going to be the variance of the moisture, which is this W prime squared, and then these other terms actually fix up the units for us in the same way that they do in the mid-latitude. No need to go into a lot of detail here. So what we find here in this simple set of equations is that the temporal tendency in wave activity is everything due with the flux, the meridional flux of eddy moisture by the anomalous winds. So this is the flux of anomalous moisture by the anomalous winds. So as long as you have an eddy flux of moisture like the diagram we saw in Rios et al., you're going to see an increase in wave activity, at least when you don't have sources and sakes of wave activity. Now we can define a second variable here that I call the available latent energy. This first equation up here has everything to do with the moisture modes. The second equation here is an equation for the Hadley cell. And the Hadley cell, it turns out that not all the moisture in the Hadley cell is actually available to be converted into kinetic energy by the moisture modes. Only the component that's actually associated with the meridional moisture gradient is. So in order to take that into account, we define this a variable called the available latent energy, or ALE for short. I found this name to be memorable enough that you all might remember it afterwards. And yeah, because it's ALE, right? So ALE is actually just the meridional moisture gradient multiplied by the half width of the Hadley cell divided by 2. It has a negative sign in here so that the ALE is a positive quantity, because this here is negative. Now, if you go to the equation of the temporal evolution of the ALE, you see that it's essentially the same one as the wave activity, but with reverse sign. So that means overall that an increase in moisture mode activity in the tropics has to come at the expense of a reduction in available latent energy in the Hadley cell. In other words, the Hadley Cell has to weaken in order for the moisture-most to strengthen, or vice versa. Because when you add these two together, you get a conservation equation in which AO plus A, it does not change with time. So you have a conservation equation that's actually reminiscent of the conservation of total energy in the system. So what does this all mean? So we can actually use the Lorentz energy cycle to show that this interaction under the weak temperature gradient approximations is equivalent to an exchange of solal mean kinetic energy, so the kinetic energy of the Hadley cell, and the eddy kinetic energy that's within the moisture-most themselves. And the equation here is on the right-hand side here, so you see that there is a relationship of the temporal tendency multiplied by a bunch of things, including the AL itself. So it's not linear in any way whatsoever, but it is directly related to one another. So the end result is that the exchanges of the kinetic energy between the Hadley cell and the eddies are proportional to exchanges of latent energy between the two. So you remove latent energy from the Hadley cell and give it to the moisture-most, and because of that, you're also taking away kinetic energy from the Hadley cell and giving it to the moisture-most. So once again, the result is that the Hadley cell has to weaken if the moisture-most are to strengthen. And the summary cycle is that you have this latent heat energy cycle in the Hadley cell where you can actually have generation of latent energy, creating AL here, but then through this flux of moisture, this eddy flux of moisture, which is associated to moisture-vortex instability, you are changing the AL and converting it to eddy kinetic energy. In the same way that you're doing that, you have to be removing kinetic energy from the solal mean and into the eddies. And because of WTG, their available potential energy plays no role in the dynamics here because the weak temperature gradient approximation does not allow for the generation of available potential energy. It quickly changes into kinetic energy. So this is the last research slide here. This is a schematic because everybody loves schematics. At least Victor's always telling me to make more schematics. So this is a schematic that summarizes this talk for today. So this is the Hadley cell with the rising branch here and the subsiding branch down here. So what we're seeing is that if there is a Hadley cell and that moisture is correlated or co-located with rainfall, you have to have a meridional moisture gradient such that moisture is a peak here and it's a minimum here. Because of the existence of a moisture gradient, this has to be unstable. And we showed that through the basic equation that you have to have instability that creates moisture-most, and the moisture-most have to tap into that instability. What results from this is that you get waves forming in this region here, and the waves start fluxing moisture away from the equatorial region and then pumping it into the subtropical area as we saw in the previous slides. Now, if you take this and assume that the equations for energy have to close, that means that the Hadley cell in itself wants to strengthen, because the only way that you can actually balance this tapping energy by the moisture fluxes, by the eddies, is if you have an energy that's trying to move inward towards the Hadley cell. So there has to be a generation of available latent energy that's purely driven by the Hadley cell itself, which means in turn that the Hadley cell, in the absence of moisture-most, would be unstable. It wants to grow in itself. So I talked to Larissa and Vijay about this, and we think that this might be a form of self-aggregation where the ITCC wants to continuously self-aggregate, and the eddies are constantly, the moisture-most are constantly ruining that and de-aggregating the whole system. Another consequence relevant for me, who I'm from Puerto Rico, is that the moisture-most actually increase the rainfall variance in the outer flanks of the tropics, between the tropics and subtropics, or the deep tropics and the subtropics. So the presence of moisture-most actually causes rainfall to be a lot more variable than it would be in their absence. So here are the conclusions in the interest of time. The big takeaways here is that Victor showed that TD-like waves and equatorial Rossby waves share similar thermodynamics and dynamic features regardless of geographical location. Our hypothesis is that this similarity cannot be a coincidence. It has to be driven by some fundamental processes that are relevant throughout the whole tropics. And the solution for that we are proposing is that the meridional moisture gradients have to be unstable throughout the whole tropics. And that means that moisture-most have to grow by flattening the moisture gradient and weakening the Hadley cell. That's where they get the energy from, and that these interactions are actually analogous to the midlatitude wave mean flow interactions, except that their main potential vorticity-like substance is the column integrated water vapor. And last but not least, I think this challenges our notion that most of the energy transport done in the tropics is done by the Hadley cell. We are hypothesizing that that's not necessarily correct, but that these waves and these vortices that are occurring in the tropics are just as important as the Hadley cell itself in order to maintain the global energy balance. So with that said, thank you all for your time, and I'll have any questions. We will go past questions.
Yes.
I was wondering, maybe a little bit there, but what's kind of the difference between those and
So the moisture modes are by definition they have to obey the weak temperature gradient approximation. That's not necessarily true in atmospheric rivers. They do, you know, through this framework, they do have an analogy similarity, and you can actually see this in maps. Like if you look at a really strong wave at a classical example which we saw last year affecting Puerto Rico and the Caribbean, they kind of look like a tropical-esque atmospheric river, but they are deep in the tropics and they obey the weak temperature gradient approximation. So the big difference would be that the atmospheric rivers have more driving force through PV dynamics, and as a consequence, they cause these flows to happen, but in the equatorial area, it's just purely variance and instability of the gradients that are causing these variations to occur. So there are some qualitative similarities in terms of how they flux moisture, but I think their governing dynamics should be different, but I would expect there to be like a spectrum in between as well.
Question from the students? And then Matt. Yeah.
So I have a question about the Hadley Cell model you used, because I'm not familiar with that. Does the model close itself at the Hadley Cell, like all the energy is contained within the cell?
Yeah.
Or it is contained within the cell?
Yeah, because you have to make it as simple as possible.
So how would the theory change given that, because of the polar amplification, once the temperature is reduced, how do you think this theory will change if you expand the Hadley Cell, like if you look at the interhemisphere rather than just the Hadley Cell?
Well, if the Hadley Cell expands, that LH term would increase. And we do also have to examine how the moisture gradient changes. But through the Clausius-Clapeyron equation, we should assume that the moisture gradient has to become steeper. So unclear what would be the end result, but this could potentially mean that the tropical waves could become stronger, it could become weaker, it depends on how this works out. But I actually don't know how this would look in terms of polar amplification, because then we are kind of like examining the tropics in isolation, but we haven't looked at how this would interact with the mid-latitudes. And there is, as you saw from the diagrams earlier, there's an intense overlap at the subtropics. So we can potentially say what happens within like 20 degrees, but after 20 degrees from the equator, it becomes a lot more complicated.
In other words, is it worth saying that the extratropical regions don't have much influence on the 0 to 20 degrees region, or they would be affected?
They would still be affecting it, because you kind of like, you know, like it's kind of like splashing it, but it's a little bit more complicated because previous views were like, well, the extratropics were the things that would perturb the tropics, but the tropics can just perturb themselves and create waves. So you can actually create moisture modes from extratropical forcing, and this could be related to some of the moisture modes that we see, but it's more of a two-way street than what people envisioned in the past, with a lot of the previous thoughts were being like, well, the Hadley Cell kind of does its own thing, or some other more recent thoughts being, well, like the extratropical forcing is really what sets the Hadley Cell itself, where we're like kind of like contesting that and saying it's like, well, it's probably more of a two-way street in general.
Thank you.
Yeah.
Matt.
It does seem like you have a really nice analogy, perhaps with the stratosphere, classical stratospheric dynamics, where the Holden picture is you have this overturning Hadley Cell. Why do you have a surf zone and theta contours are flat? Well, you have this tension between lateral mixing and overturning. Like just so maybe you have a much more moist surf zone in the tropics. Maybe that's right. But my question is about your interesting solution for the quadratic, where you have an imaginary part. That seems analogous to classical Eddy problem, where you have a growth rate. There is dvz or dtdy. You have a dw/dy. Is that how you're thinking of it?
Yeah. So in the Eddy problem, you have a thermal wind, right? So you have like a dt/dy and a ut, a thermal wind associated with that, and everything's kind of coupled to that.
Instead of a momentum gradient, you have a moisture gradient.
Yeah, instead of a momentum or a thermal gradient, you have a moisture gradient, and instead of having like vertical wind shear, you actually just have like a change from convergence to divergence associated with the rising and sinking branches of the Hadley Cell.
Can I squeeze in that nice blue solution for the aquaplanet? Do you have to have these moisture modes to get a double ITCZ? Or can you get it with a symmetric aquaplanet?
That's a good question. I would need to ask Rosie about this. We talked to her yesterday, but we didn't get to talk about that. So I don't know. Actually, it's a good question.
Would you mind switching back to the schematic you showed at the end?
Sure.
Yeah, I thought this was interesting, the idea of like a kind of like a tilting term acting on a diagonal moisture contour. So the idea of the mean meridional circulation sort of standing up a moisture contour, and then the eddy flux is tearing down that gradient exactly. So you're tilting that.
So the Hadley Cell wants to do this,
Exactly.
and the eddies want to do this, and then you kind of keep it that way in steady state.
Right. So I'm wondering if the eddies require a V prime. What part of the mean meridional circulation actually introduces the V prime? Is it some infinitesimal growth of a tiny little perturbation, or is it some action at the edges of an isolated, inhomogeneous ITCZ?
Yeah, so a small perturbation, and you know, if you have a solo mean ITCC, any perturbation in the ITCC will cause a V prime because of vortex stretching. So you're bringing the rainfall out into the latitude, so that vorticity generation from just a small displacement of the ITCC can create a vortex, and that vorticity generation creates a V prime. So it actually turns out that that V prime is actually larger than the V prime that you get from the Hadley Cell itself, or at least comparable to. So you can actually have transitions from like the wind being completely zonal to like having, you know, like a strong meridional component, which is what we see with the inverted troughs associated with the easterly. So that would be consistent. But the general explanation as to why you have this V prime is that you can actually have a small perturbation to the location of the ITCC, making it not zonally homogeneous, but just still a small homogeneity of that can just kick off the whole process.
Sure.
Yeah.
Is it typical source region like topography, or would it happen on an aquaplanet too?
It happens on an aquaplanet too. So I think just the fact that convection is spotty and inhomogeneous can just do that from the get-go would be my thought about it.
Thanks.
Right. I'm just wondering, I've always kind of thought that the atmosphere doesn't do too much poleward energy transport in the tropics, which is kind of consistent with this picture. I wonder if you've thought at all about the role of kind of zonal asymmetries in this picture.
Yeah, I mean,
it's really nice work. I'm really excited about it.
Yeah.
So also want to say that.
AC is looking at the monsoonal, the reverse mean state, which is more monsoonal. So we're starting to look at the homogeneities. I would assume that like the East Pacific and Atlantic ITCCs might be more unstable because the gradient is deeper there compared to other areas. But the fact that the warm pools also has a lot of instability as well, you know, does mean that there's some generality to it. Just as long as you have a gradient, there is activity, but I would assume that the intensity of the instabilities and the nature of how the waves look like would change depending on location. But besides that, we haven't really examined zonal homogeneities. It would be a good idea for future work.
Two more, 5 minutes, so 2 questions, and I have seen John and Matt hands on.
Victor, you should. They're all asking about the model.
Isaac, a PV view within the context of the weak temperature gradient assumption, so that you can just understand these disturbances. Seems very similar, and maybe that's it. I don't know that that's not it. But is there any extension you can see that will kind of marry the mid-latitude view of development with the tropical view of development through something like a PV?
So I looked at this in a paper that I published last year, and so what I got was that at the very best you can summarize tropical dynamics with 2 equations, which is a PV reduced to a vorticity equation, and then a divergence equation that is the WTG vertical motion one. And subsequent work that I've been looking at that shows that second equation is related to the water vapor stuff. So you essentially get a column water vapor equation and an equation for the vorticity. I have not been able to reduce that further, and that's, you know, as you see the solution, you get a pair of equations. But that's not too different from mid-latitude where you have the upper and lower troposphere treated separately. Yeah, right. So I think in the moisture mode limit of things, you can probably treat the column water vapor itself as a type of like Elias and pump flux formulation, in which case that will be the only thing. More generally, I think the 2 things are, you still have 2 equations, so I haven't been able to marry those two equations into a single one that you can use in general for diagnostic purposes. But yeah, in the very, very limit, in the very limit of moisture modes, the column water vapor itself is like a PV, so you can generalize that formulation. And I have done generalizations in the manuscript that shows that it's very similar to a PV budget, where the fluxes are actually kind of similar to like wave activity fluxes and stuff like that, but moisture based. Yeah.
Our last question, Matt.
Yeah, this might sound pretty outlandish, but there might be something to it. There was a recent eruption in, I don't have this name right, Tonga, you know that one? And so I can talk about this now. This paper was just published at Schober and GRL. They argued that there's a westward traveling Rossby mode in the stratosphere excited by an amazing injection of water vapor. You know how dry the stratosphere is, so we're talking about trivial amounts, but still, it was enough to absorb upwelling infrared, similar to, I think, what might be happening here. And in the very dry stratosphere, here's this westward propagating mode that they argue was like yours. It's astonishing. I mean, this is weird. It's in the stratosphere. But I think that maybe the dynamics might be actually right.
It's possible. Mayta and I have talked about
I didn't know what they were talking about, but it sounds like they're talking about what you have.
Mayta and I have talked about separately that you can have WTG-like modes that are not necessarily moisture-based. Mayta and I have been talking about the possibility of the existence of like dust modes and stuff, where like the radiation interactions between like aerosols and stuff can lead to similar kinds of wave activity that are completely analogous to moisture modes. But all you need is some kind of element at the atmosphere or the ocean that behaves like moisture and interacts with like diabatic heating, such as radiation or convection, and under WTG, then that will lead to its own type of wave solution. So if you have something in the stratosphere that is water vapor and that leads to some kind of radiative heating, you might have an idealized solution that's like that, or just a modification of a Rossby wave due to like the fact that you have an injection of water vapor.
Yeah.
So it's interesting. There's a lot of things to think about in there, but I wouldn't be surprised if something like
dry
that.
westward mixed Rossby gravity wave modes, dry eastward Kelvin modes, and then different from the troposphere. But now there's this one example of moisture made a difference. It's weird.
Question.
Last one.
Yeah, so lots of people, mostly Carrie Manuel, I've heard it from Adam Sobel to some extent, claim that moisture modes are the analogy to convective aggregation. This work is saying that's actually not the case, which is interesting.
Yeah.
Do you have anything, so you're kind of going against the grain in that sense. Do you have anything to say about that?
No. Maybe a few words. So I think the interesting thing is like, because the moisture modes create zonal inhomogeneities, like, you could have like different scales of aggregation where like the moisture modes themselves are a type of disaggregation, but that kind of aggregation comes at the expense of aggregation of the ITCZ itself. So in that sense, I think it would not be inconsistent with the view that the moisture modes are some kind of aggregation, but it still counters the idea that like,
So different scales.
yeah, that you can have different scales, and in fact, I didn't show this here, but one of the consequences of this analysis is that you would have a turbulent cascade of moisture in the same way that you get a kinetic energy. So you get a cascade from the zonal mean down to the eddies and then down to like the turbulent scale, because it's always propagating downscale when you have these eddies. So it's possible that the aggregation downscales, you go from like global scale aggregation to more local aggregation through this way. But I think that this is an open door to a lot of interesting future study. But I think you're right. So my thought is like,
I don't think you're wrong.
yeah, it's counter to what they're saying. It's counter to what they're saying, but maybe there's more complexity to that, right? Like there is some kind of aggregation scale. But in general, like it would be, if you ignore that part, you would be correct in what your notion is, that this goes completely counter the aggregation notion. That the moisture modes are disaggregating the mean state.
All right, sorry to keep you up.